Assalamu alaikum. Okay,
عليكم السلام
today
أستاذ.
or tonight we will have inshallah short lecture. I will give the remain part from lecture note 6. Let's complete uh, this lecture note. I upload most of the videos to the YouTube. I will upload this lecture after finish it also, because I think you will not be able to reach it also online. Okay, so let's start from here. Make a fast review for this part. So solving linear recurrence relation. This is a subject for this extra lecture. I already show you what's the meaning of linear. So linear means this equation or this recurrence relation have only exponent of 1. This means a variable a, all of the a's with exponent 1. There is no square or cubes. Homogeneous, this mean we only have one variable, which is, for example, in this example for linear homogeneous, it's only a. Okay, so this is a homogeneous. Degree, it's the last term here. It's n minus how much? This k, it's the degree. Constant coefficient means this coefficient that come with each variable, it's constant, not variable. So depending on that term, linear homogeneous recurrence relation with constant coefficient, we have this example for recurrence relation. This one, yes, it's linear because there is no exponent except 1. It's homogeneous, yes, because we have only p as variable. With constant coefficient, yes, this number consider as constant coefficient. This one, it's not linear because we have power here. This one, linear homogeneous with constant coefficient. This one do not have, or it's not homogeneous. Why? Because we have this term without variable, so we don't know which variable here, because it could be variable to power 0 or something like this. So this constant without variable, this means it's not homogeneous. This one, linear homogeneous recurrence relation with constant coefficient. This one, linear homogeneous, but without constant coefficient. This one, it's not constant coefficient. So our focus on this type of recurrence relation, linear homogeneous recurrence relation with constant coefficient. Okay, so I already mentioned this. I don't want to repeat again, but shortly, when we have recurrence relation and this recurrence relation have more than one solution, so the solution for this recurrence relation will be the summation of these two solutions. And the initial condition can be get from this one, constant multiplied by an. We will take it with examples. Okay, so the idea is to find characteristic equation for the recurrence relation. So its equation that reflects this recurrence relation. So we called it characteristic equation because its characteristic from the recurrence relation. So it's like this. You have to know K here. Then it will be first term to power K minus this term, minus this term, minus this term, because each term will go to the other side. We will take it with examples. As a review, I will give you this example. Okay, so what the characteristic equation here? We have to know the K or degree. Here is the degree. It's from degree R. So N here equal K equal 2 here when we speak about recurrence relation. So we will take this one, R or power K. Here, go to the next side. So minus, it's a plus, become minus when it's go to the other side. Minus R, instead of N, put K, which is 2. 2 minus 1, it's 1. So R power 1, it's not necessary to put power 1, okay? And this also go to the other side, so it's become minus. Instead of F, we put R. Instead of N, we put K, which is 2. Minus 2, it's become R power 0, yes? So R power 0, actually, it's 1. Anything power 0, it's 1. Equal. What remain here after we send this one and this one remains 0. So this is a characteristic equation. Sorry, power K, it's 2, so it's power 2. So R power 2 minus R minus 1. This is a characteristic equation for this Fibonacci recurrence relation. Okay. What we need from this characteristic equation? Actually, we need to solve this characteristic equation. You know how to solve the equations. You already take it in the school and even in the university, how to solve equation. For example, as you can see this equation, okay, R power 2, 2 power 2, then 2 multiplied by R multiplied by 2 with minus. This difference between perfect square. So at the end, this one, it's originally come from this shape because it's R power 2, so it's R and 2, and they have minus because this difference between perfect square power 2. So you can solve this relation. At the end, you will get R equal 2. Why R equal 2? Because power 2, it's go with 0 because this side 0, yes? So R minus 2, it's equal 0, then R equal 2. When you get this solution for the characteristic equation, R power n is the solution for the recurrence relation. So you get R power n, it's a solution for the recurrence relation or the linear homogeneous recurrence relation. So like this, we can solve it. But what if we have more than one R? Then the summation, but with constant. That's why we have theorem 1. So theorem 1, it says that if we get the recurrence or characteristic equation for a recurrence relation, then we get R1, R2 as a solution for the characteristic equation. So we solve the characteristic equation and we get all the terms R1, R2 depend on the type of the equation, characteristic equation. Then we will choose constant depend on number of the solution. If we have two solutions, then two constant, and an, which is the sequence or the solution for the recurrence relation, it's alpha 1 first constant multiplied by R1, which is the first solution for the characteristic equation, power n, plus alpha 2, it's another constant, R2, it's another solution for the characteristic equation, power n, and so on. Okay, let's take example. In this example, we want to find a solution to solve this recurrence relation with this initial values. Okay, first step is to find characteristic equation. This first step, find characteristic equation. So, what's the characteristic equation here? We have to know k equal 2. So, instead of n, we will put 2. So, this r, and instead of r, we will put, instead of a, we will put r. So, r power 2. Here, plus, go there, minus an minus 2 or minus 1, it's become r k minus power k minus 1. K is 2, we get it from here. So 2 minus 1, it's become 1, so it's r. This also go to the other side. It's minus 2 r, okay, r power k minus 2. N minus 2 become k minus 2. K it's 2, minus 2 it's 0. R power 0, it's actually 1, so we don't need it. With the time, you will know it with trying 1, 2, 3 times. You will find that you can know it without every time calculate r power n minus 2 and so on. So this equals 0. Okay, this first step, we found the characteristic equation. Okay, what's the second step? Second step, solve it. Find the solution for the characteristic equation. This quadratic equation, it's easy to solve it. We have many rules. I already mentioned the rules here, so you can click this one. It's in the slides itself. Here, how to solve it. So from this slide 31 until the end, it's only how to solve the equation that you already learned in the school, just as a review. This part from here, it's just help you to solve equation as a review. This perfect square, this shape of perfect square. You have power r power 2, x power 2, or something like this. You have a square here, and you have a square here. Usually this is a square for number. So like 4, it's a square of 2. Like 9, it's a square of 3, and so on. 16, it's a square of 4, and so on. Okay. So what's and the middle term here? Actually, it's this term multiplied by this term multiplied by 2. When you see something like this, it's a perfect square, and its solution like this. First square, which is a, plus second square, which is b here in this one. So this one equal power 2. Okay, so this is a solution. It's equal, of course, 0. Then you can solve it. You will find that a, the solution equal uh, minus b. Okay, this for the perfect square. The difference of the perfect square, it's like this. Same like perfect square, but here we have minus 2ab. Okay, then its solution actually a minus b the square. So this means the solution is this equals 0, then we have a equal b. So this is a solution for perfect square, a equal minus b, and the solution for different perfect square, it's a equal b, and so on. Okay, we have also difference of square. When we have this one, 2 square, and they have difference, so its solution a plus b multiplied by a minus b. Because when you said it's equal 0, then you have two solutions. We have a equal b, this one solution. The other solution, we have a equal minus b. Okay. What about our equation here? Our equation here, actually, it's not a perfect square. We don't have here square of any number. 2, it's not the square of any number. Okay, so how to solve it? There is a general way. It's applicable for any type, which is this way. If you have equation like this, a quadratic equation, okay, the constant of the square term, we called it a. The constant of the middle term, we called it b. And this constant alone, it's c. So we will apply this one. X means the solution of x equal minus b plus minus root of b squared minus 4ac divided by 2a. Let's apply it for our equation. This is our equation in that equation. To apply it, we need to know a. A here is 0, is 1, a equal 1. B here is minus 1, so B equal minus 1. And C is minus, C equal minus 2. Okay. Now to solve it, we will apply this one. So we will set R, we need to solve R, not X now. R equal minus B. b is -1, so minus minus become plus, so 1 minus b means 1 plus minus root of b square, 1 square minus 1 square, it's 1 minus, okay, minus 4 multiplied by a, which is multiplied by 1 multiplied by c, which is multiplied by -2. Okay. All this divided by 2a. A is 1 multiplied by 2, it's become 2. Okay, so R equal 1 plus minus means we have two solutions. When it's a plus, when it's minus. Okay, root of 4 multiplied by -4 multiplied by 1 multiplied by -2, it's 8. So 1 plus 8 become this -4 multiplied by 1 multiplied by -2, it's plus 8, all divided by 2. So it's equal actually 1 plus minus root 9 divided by 2. So root 9, it's actually 3. So plus minus 3, because root 9, this root 9, it's a 3. Okay, so we have two solutions. R1, when we have plus, so 1 plus 3 divided by 2, which is equal to. So this first solution. R2, when we have minus. So R2 equal 1 minus 3 divided by 2. 1 minus 3, it's -2 divided by 2, it's -1. So we have two solutions, R equal 2, R equal -1. Return to our question. So we have two solutions for this characteristic equation. R1 equal 2, R2 equal -1. Okay, so first step, find the characteristic equation. Second step, find the solution for the characteristic equation, like any equation in the mathematics. Okay. Third step, depending on the theorem, we said that the solution an for the characteristic equation, it's alpha 1 multiplied by, let me write it here. So the solution, we have two solutions for the characteristic equation, yes? So the solution actually like this. If we have two solutions, then an equal the alpha 1 multiplied by first solution, which is R1 or n, a plus alpha 2 multiplied by second solution power n, and so on. If we have three solutions, then plus alpha 3 R3 power n, and so on, because it's a summation of all the solution. Okay, we already have R1 and R2. So an equal alpha 1, we still don't know it. Instead of R1, put its value, which is 2, or n plus alpha 2, instead of R2, put its value, which is -1. So -1 power n. Okay. This is a solution, but it's not complete. Why it's not complete? Because we did not get alpha 1, alpha 2. We have to find the value of alpha 1, alpha 2. So this step number 4, which is find the value of alpha 1, alpha 2. We can find it, use the initial values, initial conditions, this initial values. Why? Because we can use the solution with this initial value to have two equations for alpha. So let's take this equation for A naught, which is first initial condition, and for A1, which is the second initial condition or initial value. For A0 means instead of n, we will put 0. So A0, it's equal, instead of an, A0 equal alpha 1 to power 0. And it's equal 0 here for the first term, for A naught or A0. So 2 power 0, it's 1. Multiply by alpha, it's alpha. Plus alpha 2, same issue, -1 power n. N, it's 0, so power 0. Anything power 0, it's 1. So 1 multiplied by alpha 2, it's alpha 2. Equal, how much here? A0, it's 2. So this equal 2. Okay. A1, so instead of n, take 1. So alpha 1, just alpha 1 multiplied by 2 power 1. So 2 alpha 1. Okay. Alpha 2 here. -1 power what? Power 1. So it's become -1. So minus alpha equal how much here? Equal 7. You can solve these two equations very easy to get alpha 1 and alpha 2. You have many ways to solve it. First way, you will keep alpha 1 here and send alpha 2 there. Then the value of alpha 1, you put instead of it, its value from the first equation. Second one, you can make summation or minus between these two equations. I will make summation. So by summation here, 2 plus 7, it's 9. Alpha 1, alpha 2 minus alpha 2, they can. Alpha 1 and 2 alpha 1, it's 3 alpha 1. Okay, so alpha 1 equal 3. We get alpha 1. Now, put the value of alpha 1 here in this equation. You will get alpha 2. So, alpha 1, it's 3. So, 3 plus alpha 2 equal 2. So, alpha 2 equal -1. Why -1? Because this plus will go to the other side as minus. So 2 minus 3, it's become minus 1. So we get the value of alpha 1 and alpha 2. After you get the value of alpha 1, alpha 2, put this value at the solution here. And instead of alpha, put its value. So an become equal, instead of alpha 1, 3. So 3 multiplied by 2 power n minus 1, because alpha 2, it's minus 1. So minus 1 power n. So minus 1 power n. This is the solution for this linear recurrence relation. So this is the way for find the solution. Let's take another example. In this example, we have this recurrence relation, and we need to solve it or to find solution for it. And we have this initial value. Same idea. First step, what? Find the characteristic equation. This first step. What's the characteristic equation? R power k, which is here, it's 2. So R power 2 minus R power 1, okay, minus 1 equals 0. This is the characteristic equation. Okay. Is it perfect square? No. Minus between perfect square? No. So you can use the general solution. When you use the general solution, okay, I said the general solution, it's like this. R equal minus B plus minus root of B power 2 minus 4AC divided by A square. Let me just show that I did not miss anyone. So minus B power 2 minus 4AC divided by 2A, not A power 2, divided by 2A. So from this, you can solve it. What's the A here? Here, A equal 1. Here, B equal minus 1. And here, C equal minus 1. When you apply this here, you will find two solutions like this. Let's apply it. But I will apply it quickly a little bit. Okay. So minus 1, it's 1, plus minus root. Okay. 1 power minus 1 power 2, it's 1 minus 4 multiplied by A. So minus 4 multiplied by 1, it's minus 4 multiplied by minus 1, it's become plus 4. Okay, all divided by 2A. A, it's 1, multiplied by 2, it's divided by 2. So we have two solutions here. We have first solution, it's 1 plus root 5. 1 plus 4, it's 5, divided by 2. So this first solution, it's 1 plus root 5 divided by 2. The second solution when we give the minus, so R2, it's the second solution. It's equal 1 minus root 5 divided by 2. Okay, so after we find the solution, this first step finds the characteristic equation. Second step finds the solutions for the characteristic equation. Third step, we can use the theorem to write the solution Fn as a solution. It's alpha 1 multiplied by first solution, this first solution, power n plus alpha 2 multiplied by second solution, this second solution, power n. Okay, this is the solution. From this solution, we will apply it in the initial condition here, initial condition F0 equals 0, F1 equal 1. So we will take F0. When you take F0, anything power 0, it's become 1. So 1 multiplied by alpha 1. So it's alpha 1 plus. Anything to power 0, it's become 1. So plus alpha 2, it's equal 0. This when we have equal 0, why? Because F0, it's equal 0. Okay. Now F1, same idea. Power 1 means we take it as it. So it's alpha 1 multiplied by first solution plus alpha 2 multiplied by second solution equal 1. When you solve this two equation together, you can minus the equation, or you can uh, do anything, or you can simply say from this one, alpha 1 equal minus alpha 2. So in this equation, instead of alpha 1, put minus alpha 2. So this one become like this, minus alpha 2, 1 plus root 5, all divided by 2, a plus alpha 2, 1 minus root 5, all divided by 2 equal 1. So we have only alpha 2, then you can simply get alpha 2, it's minus 1 divided by root 5. And we said from this one, alpha 1 equal minus alpha 2. So this means if alpha 2 minus 1 root 5, if alpha 2, alpha 1, 1 divided by root 5. So just simply, after we find alpha 1, alpha 2, put its value in the solution. So this becomes a solution for this linear homogeneous recurrence relation. I know maybe you feel it's difficult solution here because we have root and so on. Usually in the exam, when we put the question, we try to make the equation short, so we don't need it to take a long time with you solve it. So such equation, I think it's difficult to put it like this in the exam, but this equation, we can bring one like this one, it's okay. maybe shorter a little bit, or later we will see that we have shorter also. This doesn't mean that we bring same equation from here. Usually there's many questions in the book, and also we can make our own questions. So it's better to try to solve the questions from the book also. I will forward some suggested question from the book for you. Okay. So, example 3, same idea. What's the solution for this recurrence relation? And you have, as you can see, we have here degree 3. This means we will have equation with power 3, yes? So polynomial equation we will have, because it's depend on what's the degree here. And degree doesn't depend on how many terms you have. If you don't have this one and this one, it's still degree 3. Why? We look to last number here. It's -3, so it's degree 3. Okay? Here we have 3 initial values or initial condition. So, same idea. First, find the characteristic equation. Okay. What's the characteristic equation? R, here it's power 3, so R power 3. This minus go there as plus, so plus R 3 minus 1, it's become 2. This plus become minus, so minus 4. 3 minus 2, it's R. Okay, this plus go there minus 4. So R power 3 minus 3, this means 0. Power 0 means 1 multiplied by -4, so it will not change this this 1, because 1 multiplied by 4, it's become 4, and it's go minus. Equal 0. So this is the characteristic equation. Okay, second step, solve the characteristic equation. Here you need to focus. How to solve polynomial characteristic equation? Actually, if it's power 4, you can divide it into 2 power 2 equation. Okay, it's easy, but if it's power 3, what to do? The idea, it's like this. I will convert it to equation without power, like for example, r plus 1 multiplied by quadratic equation, something like r power 2 with something. So this one, you can solve it as a quadratic equation and so on. How to do it? To do it, actually, the idea, it's like this. This equation, however, it's not my job to teach you how to solve normal equation. Our job, it's about linear homogeneous recurrence relations. These equations, you should know it from the school, but I will tell you how to solve it. I will take each 2 terms close together. So we have, I don't need repeated terms like this. Okay, so we have r power 3 plus r power 2. Okay, so this 2 minus 4 minus 4, you can take from them like this. Minus 4, okay, as a common factor, what we have inside? R plus 1. Okay, all this equal 0. Okay, look here, we have R plus 1. Here we can say it like this. Take R power 2 outside. What you still have here from R our R power 3 plus R power 2. I take outside R power 2 as common factor. We will have R plus 1. Continue. Minus 4 R plus 1. So at the end, this one here, it's equal 0, of course. We can take common factor R plus 1. So R plus 1 multiplied by what remain here? R power 2 minus 4 equals 0. So how I solve it? I try to find common factors R plus 1 or R minus 1 from all the terms. So I take each two terms together like this and try to find R plus 1 here and R plus 1 here. Why R plus 1? Because we already can take R power 2 here outside, then remain R plus 1 here. And we can take minus 4 here outside, so we will have R plus 1 inside. So then R plus 1, we take it as a common factor, then what we still have? R power 2 minus 4. So this one equals 0 or this one equals 0. So we can take this one alone and this one alone. This one alone means R equal minus 1. This first solution. So let me name it as R1. Okay. This one. What's this one? It's different between square. You can see it here. We have a square minus a square. So it's different between two square. So what is solution? First term plus the second term multiplied by first term minus second term. So this is 2 power 2 and this is R power 2. So it's square and minus square. So it's minus square quadratic equation. Its solution simply R plus 2. Root of the first one, it's R. Root of the second one, multiply by R minus 2. It's equal 0. So from this, we have R2, it's equal minus 2. This another solution. And from this one, we have R equal 2. We can call it R3. So we have 1, 2, 3 solutions. R1 equal minus 1, R2 equal minus 2, R3 equal 2. For more information about this one, you can click this link and go to the slide here. I give you example for solution for the polynomial equation. Look, here another polynomial equation. How to solve it? It's easy. Look here. Actually, if you try here to get x or 2 outside, you will not have x plus 1. So if you have with x numbers like this, try to make each one separately. So I will make it as x power 3 plus x power 2 plus x power 2 plus x power 2. So instead of 3x power 2, I will take each one separately, x power 2 plus x power 2 plus x power 2. And this one, I will take it separately also. It's plus x plus x plus x, because we have what? 3x, yes? Plus, what remain here? Plus 1. Okay. Now let's organize it. We will take each two together. This two together. This one with this one. This one with this one. And this two together. So let's organize it. It's x3 plus x power 2. This first group. Plus here x2 plus x. Okay. Plus another x2 plus x. Plus what remain? X plus 1. Okay. So the idea, I need x plus 1 outside. So I will take from here x power 2 as common factor. What still we have? X plus 1. I will take here x outside. So x, what inside? X plus 1. Plus, I will take x outside from here. So what remain inside? X plus 1 as a common factor here. And plus here, x plus 1 as it. So we have x plus 1, x plus 1, x plus 1, x plus 1. We can get it outside. X plus 1 as a common factor. What we will still here. Okay, so x plus 1 multiply by what remain inside. What remain inside? X power 2 plus x plus x means plus 2x plus. When we take here x plus 1 outside, remain what? Divided by x plus 1. So the remain is 1. Look here. What we have? We have x plus 1. We can easily solve it. We have here x power 2 plus 2x plus 1. It's a perfect square, by the way, which is its solution x plus 1 power 2, because it's perfect square. And here x plus 1. So at the end, we have only one solution here, because x plus 1, x plus 1. So the solution x equal minus 1. This is the solution for this whole polynomial equation. So this is the idea. We will convert it to two equations. One equation have x plus 1 or x minus 1 if you find that everything minus inside, okay? Multiply by the quadratic equation that remain when we take x plus 1 as a common factor. Okay, let's continue. So after we find the solutions, you still with me or you sleep? Wake up, wake up. If you did not drink coffee, drink some coffee. We will, I think we will take another half an hour. Okay. So we almost finished this one. We will take the second theorem. Okay. Hopefully we will finish quickly. So I will not give all the details here about how to get alpha. So first, find the characteristic equation. Second, solve it. Third, we write the solution as an equal alpha 1 first solution, which is R1 bar n, plus alpha 2 second solution, which is minus 2 bar n, plus alpha 3 third solution, which is 2 bar n. So each solution for the characteristic equation power n multiplied by alpha. So we have 3 alpha. We can solve it using the initial condition. Because we have three constant, we need the 3 initial condition here. Just use this initial condition A naught for this equation. It's equal 8. From here we get it. A1, it's equal 6 from here, and we apply it for the equation. Finally, you will get the value of alpha 1, alpha 2, alpha 3 by solving these 3 equations. Actually, the easiest way it's to multiply one of them by same number as other one, then make plus or minus between them to solve it. For example, we can multiply this this one by 2. Then when you make minus, you will remove alpha 2 with alpha 2. Then later also you can solve with the third one. Actually, it will take time. So I think in the exam we cannot bring some equations that have a degree 3, maximum degree 2. Okay, degree 3, it will take time. It's not difficult, but it's time consuming. This is the issue only. So after find alpha, you put alpha in the solution. Okay. So far, we don't have a problem because all the terms here, it's equal or more than the k of the characteristic equation, of the original equation. Here, k3, we get the 3 solutions, then it's okay. Here, we get 2 solutions, and the k of the polynomial is 2, so it's okay. Here, in this example, we have 2 solutions, and this equation have degree k, so it's okay. The problem when we have number of terms in the characteristic equation solution less than the degree of the polynomial. In this case, we cannot apply theorem 2. And this happens actually if we have equations like perfect square equations and so on, because we will have something called multiplicity in the characteristic equation. What's the multiplicity? I will give you examples here. Look to this equation. This equation, it's uh, different or minus perfect square, different perfect square. So you will find only one solution. Here, it's multiplicity 2 for the solution. Why multiplicity 2? Because we have same solution 2 times, so same solution, this means. So this is a multiplicity. When you have like this, r minus 3 power 2, so it's multiplicity 2 for this r. Another equation. Look here, this polynomial equation, its solution, I already solved it with you. X, it's x power 3 plus 3x power 2, that I solved it here with you. Yes, same equation. This equation, actually, if you look, you will have only one solution. It's r power 3, so it will give us one solution. But one solution 3 times, because it's power 3 here. So the multiplicity here is 3. What do you mean by this? This cause what? Actually, if you look to the polynomial in this example, it's degree 3, so k equal 3. And terms of the characteristic equation, only 1. So t equal 1 and k equal 3. When you have t less than k, you will apply the second theorem, not first theorem. Here, if you look, we have k as 2, and here one term, so t equal 1. So also we have t less than k. So we will apply second theorem, not first theorem. For first theorem, if you look here, what we applied, all the examples we take so far, we have here two terms, and we have three terms here in this example. So t equal 3, and we have here k equal 3. So the degree equal 3, and the terms for the characteristic equation, three different solution for degree 3, then it's okay. We can apply the first theorem. Same issue here. 2 with 2 solutions. You can apply first theorem. Okay, degree 2 with 2 solutions. You can apply first theorem. But if you have number of solution t for the characteristic equation less than the degree of the recurrence relation, in this case, you will apply second theorem. What second theorem says? It's look complicated here, but I will make it as simple as possible for you. Look, when you have this characteristic equation, any characteristic equation, and you have t, if it's equal, you can apply the first theorem, it's okay. But if it's less, actually, if t less than k, the distinct solution, t less than k means the degree, then first of all, we need to look to multiplicity for each solution. So far, in this example, we have only one solution, it's multiplicity 2. Means how many times it's repeated. This is a multiplicity. It's repeated 2 times. r minus 3 power 2. So it's equal 3 and repeated 2 times. This repeated 3 times. As you can see, so far we have only one solution. Here we have two solutions. So t equal 2. But look here for the equation, it's minus 4. So k equal 4. Still we have t less than k. Each solution, R1, R2 have multiplicity by 2. It could have different multiplicity depend on, because we have here R minus 2 power 2. This first solution, power 2 means multiplicity 2. Second solution, R plus 2 power 2, so multiplicity also 2 here. We could have different multiplicity for each solution, but here they are same. Actually, this one too long to be in the exam. Usually, if we bring for this one, you will have one solution with the specific multiplicity if it's in the exam issue, okay? Because the concern of time, it's very important there. Okay, anyway, when you have multiplicity for each solution, Ri means solution, okay? If we have more than one solution from 1 to t, how many solution? Okay. Each one has this multiplicity, mi. Okay. So for R1, we have multiplicity m1. For example, m1 equal 2 or equal 3, depend on the multiplicity of the solution R. So how the solution will be? The solution an will be like this. First of all, we know that the solution from theorem 1, it's first solution power n plus second solution power n plus solution t power n. Okay, this part same like first theorem. The different with the constant here. Look how many constants we have. We will start from 1. Okay, so we have here, when you see like this, alpha 1, 0, it's not mean alpha 10. It's alpha 1, 0 plus alpha 1, 1 multiplied by n plus alpha 1, 2 multiplied by n minus 1, and so on. All this constant multiplied by the solution, first solution power n. From where this constant and how it's work? It's actually minus n minus 1 minus 2 minus, it's depend on number of multiplicity. So if we have multiplicity 2, this means multiply by n multiply by n minus 1 only. Okay. So from where come 1, 0? This only name for the constant. 1, it's come from, we are at first solution. 0 means multiplicity. Multiplicity, it's from 0 to multiplicity minus 1. So 0 1, 2, and so on to number the constant. And first part means this constant belong to the first solution. Usually, if we have only one solution, then we will take first line only. If we have two solutions, then second line will be same, but the difference, the number of the constant. It's alpha 2, 0. Why alpha 2, 0? Because this second solution and this first term of alpha, which is 0. Alpha 2, because second solution 1, and so on. Okay, I will make it simple by the example. You will see that the example will be not so complicated. It's easy. Look, we have this recurrence relation. We need to solve it. Okay, simply to solve it, same like previous, we need to get the characteristic equation. So first, find the characteristic equation. So it's k here equal to, so r power 2 here plus 6 become minus 6r minus 9 become plus 9 plus 9 equal 0. This is the characteristic equation. As you can see here, 3 it's actually 9 it's 3 power 2 and r power 2 and 2 multiplied by 3 multiply okay, r multiplied by 3 multiplied by 2, but minus, so it's different between perfect square. So its solution r minus 3 power 2. As you can see here, we have multiplicity 2 for this solution. So m, which is the multiplicity, is 2. This means we have 2 alpha, 2 constant for this solution. Okay, now understand this one. If we have 5 multiplicity, then we have 5 constant. If we have 2 multiplicity, then we have 2 constant for this solution. So for each solution, you need to know how much the multiplicity. How to know it? From the power of the solution. This the solution r minus 3 power 2. So multiplicity is 2 for the solution, and the solution r1 equal 3. Okay, so we have only one solution. So we need only first line here. This one enough as a solution. With multiplicity 2, so we don't need all this. This 2 constant will be. Okay, so will be alpha 1 0 plus alpha 1 1 n multiplied by r1 power n. So this is the solution. And the solution, it's alpha 1 0 plus alpha 1 1 multiplied by n, all multiplied by 3, which is the solution, power n. Okay, so at the end we have 2 alpha and we have 2 initial value. Then it's easy to find the solution. Just apply the initial value. Here we will take a naught, a0. So when we have n equals 0, n equals 0, then this gone. N equals 0, this become 1. So we have alpha 1 1 0 equal 1 from here, you know. We get alpha 1 0. Okay, now we take the second the second initial value, which is A1. A1 equal from the solution alpha 1 0. It's actually or let's take it as it plus, okay, alpha 1 1 multiplied by n. N it's how much? 1. So as it all 3 power 1. So it's 3 multiplied by alpha 1 plus 3 multiplied by alpha 1 0 and alpha 1 1 all equal 6. Okay, we know that alpha 1 0 it's 1, so it's 3. This become 1. So 3 plus 3 alpha 1 1. 3 go there as minus, so 3 alpha 1 1 equal 3. So alpha 1 1 divided by 3 both sides, it's equal 1. So alpha 1 1 equal 1. Alpha 1 0 it's equal 1 also. So apply alpha 1 1 here. So it's like this. And this is the final solution equal 1, because alpha 1 0 it's 1, plus n, because alpha 1 1 it's 1, so it's a plus n 3 power n. Like this, it's enough. But if you want to multiply it inside, you can multiply. Okay, 1 multiplied by 3n plus n multiplied by 3 power n. So n 3 power n. Okay, we still have another 2 solutions, then we will finish, inshallah. Another 2 examples. Okay, in this example, we have a recurrence relation, of course, linear homogeneous recurrence relation, and we need to find the solution. First of all, k it's equal 3. So here the equation k or the recurrence relation, its degree is 3, and we have 3 initial conditions. Okay, when we write the characteristic equation, it's like this: R3 minus become plus, so plus 3 R power 2. Why? Because k equal 3. 3 minus 1, it's R power 2. This minus become plus at the other side, so 3R, because 3 minus 2, it's 1, so it's R. Here, it's minus to the other side become plus 1, because 3 minus 3, it's 1, so R power 1 or 0, sorry, becomes 0, so R power 0, it's 1, equal 0. This equation, I just show you how to solve it here. I just show you, I solved it for you. So we have here at the end, x plus 1, x plus 1, so this means x power 3. Okay, and the solution x equal minus 1. So same issue here. We have, which example? This example, yes, okay, this example. We have x plus 1 power 3. So multiplicity 3 for this one solution. We have one solution, but with multiplicity 3. Okay, so we have to apply the second theorem here. So in the second theorem, it's easy. Solution, which is -1 power n. This first part, it's same like theorem 1. The difference here in the constant. We have 3 multiplicity. This means we have 3 constant. Alpha 1, 0 plus alpha 1, 1 multiplied by n plus alpha 1, 2 multiplied by n power 2. If we have 4, then plus alpha alpha 1, 3 n power 3 and so on. So we start with alpha 1, 0, then alpha 1, 0, 1, 1 multiplied by n, alpha 1, 2 multiplied by n power 2, then multiply by n power 3, multiply by n power 4, depend on how many multiplicity. We have 3, then 1, 2, 3 constant. Okay, this is the solution. We can apply the initial value to get the values of the solution. So we will take first one, A naught, apply it here. So we will have n as 0. So this as 0, this as 0, this as 1, multiplied by something. So we will have alpha 1, 0 as equal 1. So we have this one. When we have A1, this means n become 1. You can apply it here. So you will have alpha 1, 0. Okay. Alpha 1, 0 already we multiply -1 because this power 1, so it's become -1. Alpha 1, 0 multiplied by -1. So minus alpha 1, 0 here multiplied by 1 multiplied by 1. So then we multiply -1 inside. So -1 alpha 1, 1 minus alpha 1, 2 all equal -2 from here. Same issue for A2. You will get this one, then solve together. You will get what? Here you can put, instead of alpha, for example, here, I will show you. Instead of alpha 1, 0, put 1. So -1 minus alpha 1, 1. Why -1? Because I put the value of alpha 1, 0. It's 1. So -1 here. Then minus alpha 1, 1 minus alpha 1, 2 equal -2. This equation, same issue. Alpha 1, 1, we put instead of it 1. So 1 here plus 2 alpha 1, 1 plus 4 alpha 1, 2 equal -1. Okay, it's easy to solve it. We can do like this. We can set, for example, multiply first one by 2. If you multiply the two sides by 2, it doesn't matter. So this one become -2. This -2 alpha 1, 1. Then -2 alpha 1, 2 -4. I multiply everything by 2. Why? Because I need to make summation. Make summation for both. Okay, so minus 2 plus 1 minus 1 minus 2 alpha with 2 alpha 1 1 gone. 4 minus 2 it's plus 2 alpha 1 2 equal minus 4 minus 1, it's become minus 5. So from this, you will find that alpha 1, 2 equal minus 2. Why minus 2? This one become there as 1. So minus 5 plus 1, it's minus 4 divided by 2, it's minus 2. And in any of this equation, put instead of alpha 1, 2, minus 2, and instead of alpha 1, 0, 1, then you will get alpha 1, 1, and you will find it as 3. Then put the numbers here. So it's 1 plus 3n minus, because this minus 2, minus 2n multiplied by minus 1 power n. This is the solution for this characteristic, this recurrence relation. Plus example, we finish. This example, I will make it more quickly because we already now know all the tricks. Just let us check it. We have k here as 4. So the degree is 4. However, as you can see here, we have only 1, 2 terms, but the degree is 4. Okay, degree depend on last n minus how much last value here. Okay, first find the characteristic equation. It's Rn, so R power k, R power 4 plus become minus 8 R. 4 minus 2, it's R power 2. Here you have to focus. It's not R power 3. It's R power 2. From where I get, instead of n, put the value of k, which is 4. Minus 2, it's become 2. Okay, so power 2, second term. Third term, we send this one there. It's minus 16 become plus 16. R power, instead of n, put the value of k, which is 4 minus 4. So it's R0. R0, it's 1. 1 multiplied by 16, it's 16. Okay. So we have this characteristic equation. And from this characteristic equation, it's actually easy equation. It's not the equation power 4. We actually, if you think about it, this 16, it's 4 power 2, and this R power 4, it's R power 2 all power 2. So this equation, you can consider it as a different square, perfect square, a different perfect square. So it's actually R power 2 minus 4. Why minus? Because we have here minus. Minus 4. So root of this part, all power 2. Okay. Now forget this power 2. Look inside here. What inside? It's different between two square because 4 is a square. R power 2, it's a square. So what's the solution for different 2 square? It's r minus 2, the root of the first one, the root of the second one, multiplied by r plus 2. This is the difference of the square. All put this inside power 2. So you can put this power inside, this power 2, this power 2, and remove the power from outside. So we solved the equation. As you can see here, we have here solution and we have here solution. This solution R1 equal 2, but with multiplicity equal 2. So multiplicity 1, it's equal 2 here. And this other solution come from here. R equal minus 3, R2 equal minus 3. This solution also, because we have power 2, so it's also with multiplicity M2 equal 2. So we need to apply theorem number 2. Okay. Easy. Consider each one separately. What's the solution for first one? First one, R1 power n multiplied by the constant. What's the constant? Alpha 1, 1, okay, plus alpha 1, 2 multiplied by n. How many 1? We have multiplicity 2, then 1, 2, enough. So this first solution, first part of the solution. Second part for R2 power n multiplied by constant. What's the constant? Alpha. Now, because R2, it's alpha 2, 1, or we can consider it 2, 1 or 2, 0. This 1, 0. Let's start counting from 0. 1, 0, 1, 1. It's just a name for a constant. You can name anything just to differentiate the constant. Okay? So, this constant 1, 0, this constant 1, 1. Okay, this constant 2, 1 plus constant or alpha 2, 2, 0, alpha 2, 1 multiplied by n. If you have more, now we don't have more, but if you have more, plus the second constant n power 2. If you have more, plus the second constant n power 3, and so on. But we don't have this because we have multiplicity 2, so we have two constant only multiplied by the solution R2 power n. So we have this part, this solution, the solution for an, it's equal first solution plus second solution. So at the end, by the theorem, an, which is the solution for the recurrence relation, equal first solution, we write it here. R1, it's 2. So 2 power n here. R2, it's minus 2. So this second solution, but instead of R2, we will put minus 2, its value, yes, to power n. You can use this initial condition and apply the initial condition to get alpha 1, 0, alpha 1, 1, alpha 2, 0, alpha 2, 1. Because they are 4, then you need 4 initial condition, 1, 2, 3, 4 to solve it. This will take time. At the end, this is the values. From this values, apply these values here, and instead of alpha, its values. Then this is the solution for the characteristic equation. This one is very long. I think it's difficult to bring this long in the exam. Almost it will never happen, inshallah. Okay, so that's all. So far we finished. If you have any question before I end this, actually I'm exhausted now.
Teacher,
So
how we get the
if you have any
video?
question, please ask.
How do we get this video, teacher?
I did not hear you. Repeat. What you are asking, or okay, if there is no question, then
Teach you
yes,
how we did get this video.
I will put this video inshallah on the YouTube. Okay, I already give you the YouTube channel in the Telegram group. Then inshallah I will put this video tonight on the YouTube, inshallah. You will find it in the playlist of discrete mathematics. Okay?
Teacher,
Yes, teacher.
Yes, Anwar.
how many questions in exam?
It's not decided yet. I will tell you later when we finish to put the exam, because we did not put the exam yet.
Okay, sir.
Okay. So,
Good
good
night.
night. Good night. Assalamu alaikum.